right, so now we're going to be talking about self-interactions. So earlier we talked about the Green's functions for the Klein-Gordon equation. Okay, again, the Green's functions were these things that helped us describe interactions between peaks. Right, we can really do, if we talked about this mathematically, the Green's functions are the things that describe interactions because they are the waves that interact with one another. Right? The peaks that stand alone don't interact. We need to have the Green's functions in order to describe the interactions between them. And so in this video, we're going to talk about self-interactions. And we're going to start off by talking about, by coming back to this idea of the pendulum approximation, right? So recall in an earlier video that we had talked about the potential looking like this. No, actually, I need to put a constant like this. And so, self-interactions. This was the pendulum. This came from the idea of accounting for a pendulum activity. And so what we could say is that the derivative of the potential with respect to phi, well, that's just 1 over, or times 4 times 4 times that cubed, right? Well, 4 over 4 factorial, if you do that, that's just 1 over 3 factorial, like this, okay? And similarly, our our general function our general solution to our Klein-Gordon equation looked like this. Where we have the height of each delta function, as being this. That was probably a little bit too large. D V phi d phi, and then our special functions that constructed our delta functions. Oops. Okay. And so, okay, so what can we say here? Well, this here actually becomes d4y times 1/3 factorial times 3, or to the 3rd power. And I'm just gonna suppress now this because the book will do this, right? We want to keep in mind that there's a lot of suppression going on in physics, just to keep the notation short so that it doesn't become, so that's not too overwhelming, which is bad and good, right? The suppression of notation is bad in the sense that you don't really fully understand what's going on sometimes. So you kind of really have to understand to be able to read these books. But at the same time, it would be the book would be double as thick if you put everything into these equations. But anyways, so what we have is we have this here as being our general solution to our Klein-Gordon equation. Okay. Now we're going to do something a little bit interesting here. We're going to say that The general solution, the general solution is, this is sort of a side note, but not really. The general solution can be broken down into powers of this constant. Okay. And this is going to be this is going to be very useful to us. This is what the book calls perturbing or a perturbation method. Okay. This method is commonly used because oftentimes we can't find explicit solutions for these equations. And so what this is equal to is pi 0, or lambda to the 0th power times, lambda to the 0th power times phi 0 plus lambda to the 1st power times phi 1 plus lambda to the 2nd power times phi 2. So by orders of lambda, we are adding these solutions together, okay? So this is like taking a complex function and not decomposing it into delta functions, but just decomposing it into simpler functions. And those simpler functions can be decomposed into delta functions, right? So there's a lot of decomposition going on here, but there's also, this is going to be really helpful when it comes to more practical stuff in experiment and so forth. And so, and again, these are all functions of x, right? So to be more complete, I'll actually do this. To be more complete, we have x plus phi to the, or lambda to the 1st power, the first perturbation plus lambda to the 2nd power and the 2nd perturbation on phi, and so forth. So that's what this looks like. And so what we can say here now is that if our Klein-Gordon equation, or our Klein-Gordon operator, operates on our solution, well, our solution is just all of this, right? So we can actually take all of that. I'm just going to take all of that, and I'm going to copy paste it. Actually, I'll just draw it in. It might be quicker. We have phi 0, because anything to the 0th power is 1, plus lambda phi 1 plus lambda squared phi squared, or phi 2, and so forth. Well, this is equal to 1 over 3 factorial pi times our potential, right? Because what we're saying is that is this essentially m squared times phi is equal to our derivative of our potential with respect to phi. And we've seen this, again, I don't think I wrote it down here, but we've seen this multiple times, right? Because we're looking for the solution, the general solution that gives us this potential, or the derivative of this potential. And when this is a Green's function, this gives us a spike, right? But now we're looking for general solution, right? So I'll go ahead and erase that. I don't want this to be too cluttered. So I will replace that now with the same thing. So phi plus, right? Okay, so we haven't really done much yet. Oh, we have to cube that too, because that's the derivative of the potential. And then essentially what you can do is cube this. You just use FOIL methods. Right, so what do I mean by that? If that's something you don't recall from basic algebra, that means phi 0 plus lambda, phi 1 plus lambda squared, phi 2. What this essentially is a something of a Taylor expansion, but not quite. Right? And we do the same thing like this. And we do that 3 times, right? Because of this 3 right here. So what we end up getting, really, because what you're going to have to do is you're going to have to multiply this guy with this guy, and then this guy with this guy, and then here with here. And then you're going to do the same here, and the same here, and the same here. And then you're going to do this one with him there, and there, and you can do this on and on and on. I'll get to the point though, because the point is more interesting than doing the monotonous math behind that. Is that d mu plus m2 times phi 0 plus lambda phi 1 plus lambda squared phi 2 and so forth is equal to 1/3 lambda 0 cubed plus 1/2 lambda squared phi 1 or phi 0 and phi 1 plus 1/2 lambda cubed phi 0 phi 1 and so forth. And what this tells us now is that, well, this operating on this one is going to look like d mu plus m squared times phi 0 is equal to 0, because we have no terms in here that have contain a phi to the 0. So so we're collecting terms on the order of phi to the 0. So we can do the same thing here, plus m squared on phi 1. And, well, actually, I'm going to multiply that by phi 1. All right, well, that's going to be 1/3 factorial times phi. Okay, well, we can cancel out the phi's. Shouldn't have done that. Well, we can divide both sides by phi. And this should actually be a 0. And what we end up getting, if I just clean this up a little bit, is that d mu plus m squared phi 1 is equal to 1 over 3 phi 0 cubed. And we can keep on doing this. We're just, so here we're collecting terms of order pi 1 or lambda 1. And we can collect terms on order of lambda 2 and 3 and 4 and so forth. So this is interesting to us because we're able to see now how we get this build-up effect. We're building up from 0, and then we get 0 here, and we can get phi 1, get the solution for phi 1. Here, this is, so this is actually, so the next one's going to have phi 1 in it, and phi 0 in it, because that's right here. And that's on order lambda squared. Then we're going to get the thing of order lambda cubed, and we can build up from there. So we can find out what the solutions are, what all of these are, and then we can add them all up in this way to get, or we can add them all up in this way, right, to get our general solution. Okay. Now, what's interesting is that when we start talking about interactions, right, so the interactions again are going to be, or they're going to look like this. d4y times 1/3 pi cubed y mu phi s x mu y mu. Right, so this is where our interaction terms are going to come from. And our interaction terms are going to do basically what this interaction term is we're going to be able to use this, right? This is a thing that again describes our delta functions. This is the height of each delta function and gives us the general solution. Well, since we're able to calculate this now in terms of different perturbations, we can actually plug those perturbations in to here, right? And what we'll be able to get again is the same pattern, right? So phi 1 of x mu is going to be, here, I'll actually write this out explicitly. I will go ahead and copy this actually. Let's see, so select, copy, and let's go to a new page, and then paste. So let's blow this thing up here. It's this guy right here. That's going to be phi 0 plus pi, or lambda phi 1 plus lambda squared phi 2, and so forth, times phi s. And we have our 1/3 lambda and our d4y like this. And all of this is going to be equal, well, our general solution, just like we said, was, just going to move this over here. Our general solution, like we said, was phi 0 plus lambda phi 1 plus lambda squared phi 2, and so forth. What we'll be able to see now is that when we do this multiplication, right, we're gonna get this times this. So our lambda 1, or our phi 1 lambda 1 is going to be the integral of d4y. Let's see here, lambda over 3 pi. This has to be squared or cubed because we cubed it right here. And so this is going to have to be cubed. Like this. And we'll be able to sort of iteratively do this by saying, well, we can, okay, well, first we can cancel those out. We can get what our phi 1 looks like in terms of our interaction function. So keep in mind what we're doing is we're really just, we're decomposing our function, so here's, say, our function, phi g, we're decomposing that into simpler simpler functions. Say, here's our phi 1, and then say our phi 2 maybe looks like this. And these are just, these could be thought of as simpler functions. We're doing that, this is sort of a Taylor expansion. And we will be able to find each one of these, again, by means of this delta function and by means of the previous solution also that we got. And so just to continue this a little bit more, again, these are all functions of x mu. So this is a function of x mu, d4y. This is going to be 0 and like this, and then phi s. Okay. And then we're going to have 1/2 term out here, or 1/2 factorial, when we multiply all of this out. Okay. Well, we can keep on doing this. What's very interesting is that we can keep on doing this for, well, actually, we can keep on doing this, but we found out here, right? We found out right here that this is the same thing, right? This is just phi 1. This is phi 1. So what does that mean? That means that phi 2 is equal to d4y phi 0 squared at y mu, and then and then 1/3, okay, I don't know why this keeps on going to my eraser, 1/3, and this is going to be phi 1, no, phi 0, sorry about that, my iPad glitched for a second. This is going to be phi 0, 3, like this, and we actually need another term here. This gets a little bit confusing because we need x mu okay. And then we need to cap this all off. Like this, and we have that 1/2 factorial out front. So we have this just in terms of phi 0, which is very interesting because what this is telling us is that we really just have, we can rewrite our second perturbation, or our second order perturbation, in terms of just our phi zeros. We don't even need to refer to phi 1s. So, and also what this is telling us is that we have self-interaction terms, right? Because each one of these is a perturbation, and those perturbations are self-interacting at these different at these locations, x prime and x not prime. Okay, that's what the self-interactions mean, right? Is they mean that we have phi 0, or we have a cubed interaction going on here at this point at y prime of mu, and we have a squared interaction, so that it's interacting with itself twice or the field is interacting with itself twice at this point. So it's interacting with itself 3 times here and 2 times at y mu. The way the book likes to talk about it is it says, okay, well, here's x, the point x mu in our field. And this is on page 250 at y mu, there's self-interaction going on. And we have this, our phi s, our interaction term. And then we have 3 interaction terms. Going on here. Okay. And these are all determined by S. This should actually be Y, I believe. Yes. And that's an X. No, this is, I have that mixed up. This is an X. And this is a Y. So this is y mu prime. So these are at y mu primes, and this is at x mu y mu. All right, so we have these interaction terms. These are what's called self-interaction terms, okay? Because we have these powers. We have these powers occurring. And yeah, so again, just as a quick reiteration, I don't really know how far I am in the video because it glitched at that one point. But the point here again is that we have these, just to reiterate one more time, we have these delta functions. The delta functions are describing particles. In the case of self-interactions, we started off really just by claiming that we could perturb the general solution to the Klein-Gordon equation. And each perturbation is interacting with itself to some degree, and that degree is given to us by these powers, right? So and that essentially comes from this being cubed, right? So we get these self interactions at these points. So when we approximate our solution by these different phi's, those approximations interact with each other to get our overall function, or to get our general solution to our Klein-Gordon equation. Okay. So in the next video, we're going to be talking about Yukawa interactions. Yukawa interactions are interesting because they're going to help us to understand how scalar fields and Dirac fields will interact with one another. And that's going to be very important, especially when you get into higher level physics, where you talk about, or where you end up talking about areas in which the Higgs boson interacts with particles like electrons to give them mass, for example. As you've heard, the Higgs boson is sort of the mass-giving particle. And these Yukawa interactions are going to be important in understanding how scalar fields, again, the Higgs boson is really the only scalar field we know so far, how scalar fields interact with the Dirac field. So with that being said, I don't know how far I'm in this video because I had to start my timer again when my iPad glitched. But that's the overall point. And again, if this is the kind of stuff you're interested in and you like this kind of stuff, then I would please hit that subscribe button and visit my Patreon page if you're interested in that. So I'll see you guys in the next one. Bye.